Hello and welcome to this lecture. We are going to close out the study of logarithm function with a bunch of problems. So, every time you introduce a new function, because we are studying the calculus of those functions, right. So, we have to worry about how to evaluate limits using that function, how to evaluate derivatives using that function, and how to do integrals using that function. So, now this is a new tool in our bag. So, let us put it to use and try and see what we can do. So, log, for instance, has this magical property of converting multiplication to addition, and that can be put to use in very creative ways. And then it also has the property that the derivative is 1 by x, and then it's also the inverse of e power x. So all these three properties are crucial for the logarithm function, and you can use it in very creative ways, as you'll see when we go along. Okay. So the first set of problems is on limits. Let me take the first one and then talk about it. So it's asking you to do limit as x tends to 0 plus root x log x. I'm sorry about that. Okay, so the problem we are trying to do here is limit, let's do black, limit as x tends to 0 plus root x log x. Okay, couple of things to remember about log x. I think you recall the function, right? It's plotted like this, log x versus x, right? This is at 1, and at 0 it goes to minus infinity, right? It goes off to minus infinity. At as x tends to infinity, it goes off to infinity. Okay, so it's a function that has a picture like this. So you should quickly visualize this picture in your mind. Only then you'll understand what's going on. So what about root x? So this is log x. Sorry, maybe I should write log x here. This is log x. So what about root x? Root x is 0 at 0, and then it sort of goes again to infinity, but at 1 it is 1, isn't it? So root x will go like this. Okay, sorry about that. So it will go off. Okay, so maybe I should draw it a bit differently. So root x will also go to infinity, and it will go to infinity much faster than you can imagine with log x. So this is root x. Here it's 1, it's irrelevant, but at 0 it is 0. So why do we say 0 plus here? Because clearly log x is not defined for x negative, right? So you have to come only from the right direction for the limit. So root x log x. Okay, so root x is tending to 0, and then log x is tending to minus infinity. This is a 0 into infinity form. Okay, so this is an undefined form. Okay, so you need to be careful about figuring out what the limit is. Okay, so you need to see as x tends to 0, which is going faster. Is root x going faster, in which case this will go off to 0, or if log x is going faster, this will pull itself to minus infinity in some sense. So something like this is what's going on here. Okay, so in all these kind of scenarios, one very basic and important tool is to use L'Hopital's rule, right? So L'Hopital's rule is very useful, and for that I need a ratio. So I can sort of manufacture a ratio here. So I can make this as log x divided by 1 by root x. Okay, so now I have numerator tending to minus infinity, denominator also tending to infinity, right? So both are tending to infinity, and I can use L'Hopital's rule. So if you use L'Hopital's rule, you see that so this guy has this problem. So you see that limit as x tending to 0 plus root x log x is limit as x tending to 0 plus of the derivative of log x, right, log x prime divided by 1 by root x prime. Okay, so this log x prime is 1 by x, 1 by root x prime is power, this x power minus half prime, and that is minus half x power minus 3 by 2, right. So that's what I need to write here. So it's minus half x power minus 3 by 2. So it's important. So this will go up on top, and you will get x power 3 by 2. This minus half will become minus 2, and you will have by x, and that will simplify to get you minus 2 x power 1 by 2. So now limit as x tending to 0 plus minus 2 x power 1 by 2. Now I can substitute, right? So there's no problem here. This goes off to 0. So root x log x goes to 0 as x tends to 0 plus. So watch out for this confusion. See, this is going off to infinity, that's going to 0. You don't know as x tends to 0 very closely which is going faster or smaller, slower, and that will determine whether the answer is infinity or 0. And using L'Hopital's rule, you can do a fine grained, you can find out how that works out. Okay, so that's the first problem. The second problem, let me just get rid of this guy, sorry. The second problem is a very important and interesting and historically very relevant one. Okay, so this 1 plus a by n power n limit as n tending to infinity is a very important limit, and in theory and also in history, there is a good reason for it. So let's try and evaluate it. So you're doing n tending to infinity 1 plus 1 a by n raised to the power n. Okay. Okay, so once again, one needs to see how to do this carefully, right? So you have to be very careful. So if n goes to infinity, this is tending to 1, right? That's okay, and that guy is tending to infinity, right? This is going off to infinity. So it's very tempting to say 1 raised to the pi infinity is 1, so this will tend to 1. Okay, but you have to be very careful. So this is 1 plus a by n raised to the power n. So this n will also interact with this guy, right? And this is just going as 1 by n. So there may be some cancellations here, and you may get something from here. Okay, so this is a slightly more tricky situation. You need to figure out what's going on here. Okay, so the way we have developed logarithms and exponential, we can use log now and exp now, right? So limit and continuous functions can be interchanged very easily, right? So we know e power x is continuous, log x is continuous. So instead of considering this limit, we can even consider the first thing to do is to make this substitution, let's say m equals 1 by n. Okay, and then you get that this limit is the same as limit as m tending to 0, right, of 1 plus maybe I should do this way, x equals 1 by n. Okay, and then limit as x tending to 0. So let me not write even x equal to 1 by n. So you see that these two limits will be the same. So I want to argue this. I want you to think about it very carefully. So these two limits will be the same. So it's almost like a x is becoming 1 by n type of thing, but except that x is like a continuous variable now. It's not a discrete jump, but the continuous to discrete thing is okay because all these functions are continuous. Okay, so that part is something that needs technical justification, but I think at this level for our course we can simply say x is 1 by n. So if x is 1 by n, x is going to tend to 0 and 1 plus ax and then power 1 by x. Okay, so now here again you have this confusion. As x tends to 0, you have a 1 power infinity, and this is actually this kind of tending to 1 power infinity is still an undefined form. Okay, so this is an undefined form. Okay, as n tends to infinity. So you can take first thing you can do is to take log of this and look at the limit as x tending to sorry. You can take the log of this and look at the limit as x tends to 0, right? So what is log of this? So log of this, log of 1 plus ax power 1 by x is 1 by x log 1 plus ax. Okay, so what I'll do is I'll take limit as x tending to 0 of log of 1 plus ax power 1 by x. Okay, supposing I find that this is some L. Okay, so this limit is some L. What is limit as x tending to? So this is the main result. If this is true, then limit as x tending to 0 of 1 plus ax power 1 by x is going to be e power L. Okay, so this is an important result that we are going to use, and this is very powerful quite often in evaluating limits. So you see there are lots of ideas here that are coming around, and you need to keep track of all of them. I am doing this limit with n as a discrete variable, right? First thing I do is convert to a continuous variable and do this 1 by n conversion. So that x tending to 0, 1 plus ax power 1 by x. These two are the same. You use continuity of these functions and show that these two are same. Now this is still an undefined form, and I want to take log, because only when I take log I will get some reasonable behavior with this. So I get 1 by x log 1 plus ax. Okay, but I'm claiming that after log, if I take a limit, and if I want to figure out what is the limit without the log, then I can do the inverse of that. Again, this follows by continuity of these functions, log and e power and all that, and the limit place, you can exchange limit and function when you have a continuous function, right. So that's all that's going on here. So you can do this. So these ideas are very important, and even if the technical proof is not clear, you should know how to use them. Okay, moving from discrete to continuous in the limit, and continuous variables for finding a limit. As long as you use continuous functions, that's okay. And then taking log and then doing the limit, and then going back by doing e power l. Okay. So now it turns out, is this limit easy? It turns out it's not too bad. Okay. So limit as x tending to 0 log 1 plus ax by x, right. So this is the limit, these two are equal. So this is the limit. Now here I have a 0 by 0 form, right. So x is 0 means it's log 1 is 0, and x denominator is also 0. So I have a 0 by 0 form, so I use L'Hopital. L'Hopital's rule can be used here. So I get that this is the same as limit as x tending to 0. Derivative of log is 1 by 1 plus ax times a divided by derivative of x is 1. So you get here now a very easy limit as x tending to 0, a by 1 plus ax, and that is simply a. Okay. So now what is the original limit? Limit as, which implies, using our result, limit as x tending to 0, 1 plus ax power 1 by x equals e power a, which implies this limit is also e power a. Okay. So this is the reason why this is very famous, and a lot of people take this as a definition for e power x, limit as x, not x, n tending to infinity 1 plus x by n power n. Okay. So a lot of people will take this as a definition for the e power x function. It's limit as n tending to infinity 1 plus x by n raised to the power n. Okay. So this is a very useful definition, and there are lots of interesting properties that this definition itself has. We didn't take this approach in this class. We took a different approach to define e power x, but good enough that finally this limit is also working out to be the same. Okay. So I hope that was clear. In this problem there were quite a few techniques that we saw: how to convert a discrete limit to a continuous limit using continuity, and then how to take log inside a limit, and then how to go back and undo the log using the e power x. Okay. Now the other problems I am not going to do in great detail. So this log 1 by x by log base 2. Okay, so maybe I should do this also, because there is a base change here. So let me do the third problem. So limit as x tends to infinity log 1 plus x by log base 2x. Okay. So the critical thing to do anytime you have a log which is some base other than log e, is to simply write it as log x by log 2. Okay, first get rid of any other base, okay, before you do anything. So log 2 is just a constant. So this is the same as log 1 plus x by log x times log 2. Okay. Now if you do limit as x tending to infinity, you are going to get infinity by infinity form. You can do so limit as x tending to infinity log 1 plus x by log base 2 x. You can do L'Hopital again because of the infinity by infinity form. So I use L'Hopital's rule. So I get the derivative there, 1 by 1 plus x by 1 by x, and that is just x by 1 plus x. So limit as x tending to 0. I'm sorry, I keep forgetting to write the limit. Let me write it carefully. Limit as x tending to infinity, limit as x tending to infinity, x by 1 plus x, and that you know is going to go to 1 by x plus 1, and as x tends to infinity, this will go to 1. So limit as x tending to infinity log 1 plus x by log base 2x is actually 1. Okay, I'm sorry, there is a log 2 that I forgot throughout. So this is log base 2 is 1 into log 2. So the answer will end up being log 2. So there is a log 2 here, right? So this limit itself is 1. So that gets multiplied by log 2. So you get just log 2. Okay, so that's the answer for that limit. So this base substitution is base change is very simple. Just forget about this base 2, go to log x by log 2, and then you're okay. Okay, so let's look at this last problem here, the number 4 problem, limit as n tending to infinity 2n power 0.1 plus log n by n power 0.1 plus n. So you should remember this log n as n tends to infinity goes slower than any power of n. So n power 0.1 goes faster than log n. So as n becomes really large, you can ignore log n compared to n power 0.1. So the other way to argue is you take n power 0.1 common outside. So the way you can write it 2n power 0.1 plus log n by n power 0.1 plus 1. So you can write it as 2 plus, you divide every term by n power 0.1 and then you get 1 plus 1 by n power 0.1. So as n tends to infinity, this goes to 0. Okay, why? Because log n goes slower than any power of n. So log n will go to infinity much slower than any power of n. So as n tends to infinity, this will go off to 0. This will also go off to 0. So in the limit, this will tend to 2. Okay, so it's a very easy limit, but just to tell you the comparisons. So basically this, you can ignore log n when compared to n power 0.1. For really large n, you'll see n power 0.1 will dominate log n. Okay, so that's an important factor, remember. Okay, so that's about limits. So we saw 4 problems, lots of interesting ideas. The moment you have log, there's so much more power you have, so many more problems you can deal with. Okay, so let's move on to derivatives. This is slightly easier. So I'll do the first, third and the fourth problem really quick. The first one is very quick. So the way to do that is, so you have a function f of x is log 1 minus x by 1 plus x. Okay, so it's very tempting to use quotient rule and log and all that and try this. So if you do that, it's a lot of work, but one very easy property is to write it as 1 minus log 1 minus x minus log 1 by 1 log 1 plus x, because this is log a by b, so it's log a minus log b. So once you write it like this, f prime is very trivial. Log 1 minus x derivative is 1 by 1 minus x times derivative of 1 minus x, which is minus 1. And then this is minus 1 by 1 plus x times plus 1, right? So it's a very easy derivative. And so you get minus 1 by 1 minus x minus 1 by 1 plus x. You can do this very quickly. It will be minus 2 by 1 minus x squared. Okay, so you see how easily the derivative works. You use the property of log. If you don't use the property of log, you'll be going round and round in circles, and that will take a long time. Okay, so this problem, this third problem, is also something where log will help you. Okay, so it doesn't look like there's no log here. It seems like log won't help you. You can use quotient rule, whatever, and do a lot of complicated calculations. But if you use log, the answer will come out very easily. Okay, so f of x is x power 6 times what, x plus 1 whole cube times x plus 2 whole squared, or what? Yeah, and then x plus 3 whole squared times x plus 5 power 10. Okay, so at this point it seems like log is not useful, but then if you take log, notice what happens. Log f of x is 6 times log x plus 3 times log x plus 1 plus 2 times log x plus 2, right, minus 2 times log x plus 3 minus 10 times log, let me write it more carefully, 10 times log x plus 5. So notice this neat little way in which this got this changed into something. And now if you take derivative on both sides, you will get 1 by f of x times f prime of x, right? So this is log f of x, so the composition rule will kick in. So you do 1 by f of x times f prime of x. Here you have 6 by x, 3 by x plus 1, 2 by x plus 2, minus 2 by x plus 3, minus 10 by x plus 5. Notice how easy it is to do it like this. And then f prime of x, you have to multiply by fx, and that is just this big mess, and I'm not going to do it. So you can write it very easily, right? So at least there's a much easier way to find this solution than using quotient rule and running around and round. You won't get to any comfortable answer. I hope this is easy enough for you to see. Of course, there is a simplification here. It may or may not work out very easily, but at the end of the day, we at least have an expression. Okay, so that's the use of log in these kind of rational product forms to get a simple answer. So here is another one, x power 2x log x. Okay, so one very interesting function is x power x. How do you do derivative for x power x? It's a lot of people will be tempted to use the x power a rule, but that a is supposed to be a constant. It cannot be a function of x. So if you have x power x, here again log is very useful. So you can do log fx is x log x. Okay, and then if you do derivative is 1 by fx f prime of x equals this derivative is x times 1 by x plus log x times 1. So that is just 1 plus log x. So you multiply by f of x on this side, that is x power x times 1 plus log x. Okay, it's a nice thing to remember. So the exact function that's given here is I think it's x power 2x times log x. Nevertheless, the same trick will go through. If you do log fx, you get 2x log x plus log of x, right? That's okay. All these things can be very efficiently and differentiated. 2x into 1 by x plus 2 log x into 1 plus 1 by log x times 1 by x, right? So that's all. So you get a very simple form, 2 plus 2 log x plus 1 by x log x. Okay, this of course multiplied by f of x, which is x power 2x log x. Okay, so these kind of calculations can be done very easily. So anytime you have an x in the power, log is going to be useful, whether you're taking limits or you're doing derivatives. Anytime you have a lot of products like this, once again log is very useful. Okay. Now we move on to integration. There are some 7 problems here. I'm not going to do all of them. The theme is usually very simple. We have e power x and log x, but now we have this additional fantastic formula that we have the antiderivative of 1 by x, right? So antiderivative of 1 by x is log mod x, isn't it? Log mod x plus c. So we can use this log mod x idea, but don't forget the mod. The mod is important. Remember the calculation where I showed you how the mod works out. So log mod x is the answer for antiderivative of 1 by x. So now we can use it in clever ways. Look at the first problem. I'll do the first problem. It's a simple one. Integral 2 to 5 x by 1 plus 4 x squared, right? Integral 2 to 5 x by 1 plus 4 x squared dx. Okay, so immediately you see this pattern of derivative, right? There is an x squared here and the derivative here. So a very tempting thing is to do 4u squared, 4x squared, I'm sorry. So du becomes 8x dx. Okay, and then notice this x dx. So this becomes integral, this is x equals, this is u equals, if you put 2, 17, if you put 5, you're going to get 101, right? And then x dx is du by 8, so you get du by 8u. Okay, now you have du by u, so this is 1 by 8 log mod u between 17 and 101, and this mod is just, it's just everything is positive here, so 1 by 8 log 101 minus log 17. So you can also write it as 1 by 8 log 101 by 17. Okay, so easy enough, and you notice how this x by 1 plus 4 x squared we couldn't do before. Because of log being there, you're able to do antiderivative for x by 1 plus 4 x squared. Okay, so many of the other problems will work like this. So you notice here also you have e power x 1 by 1 plus 4 e power x. You can notice very quickly that this problem also has a derivative here. So you put u equals 1 plus 4 e power x, the problem will be done. Okay, what about this one, 1 by x log x? It looks like this is different, but anyway, this is also very easy. You notice here log x, the derivative is 1 by x, right? So you can again put u equals log x, and this also becomes something like this. So the antiderivative will be log of log x We just now saw that also in the other context. So, log of log x is the problem, the idea here. So, what do you do with 2 power x? Maybe I should comment on that. How do I tackle 2 power x? Okay. So, 2 power x is integral 2 to 5, I think. Is it 2 to 5? Yeah, it just does not matter what it is. 2 power x dx. Okay. So, the idea here, you should always convert a 2 power to e power something. Okay. So, this is the same as e power x times log 2. Okay. So, this I think is something that is very important. So, x times log 2 is actually log 2 power x, e power log 2 power x is just 2 power x. So, this is the same as 2 power x. Okay. So, once you have this, everything is very easy, because antiderivative e power x log 2 is trivial, and then you do this, you get the answer. Okay. So, 1 by log 2 times e power 5 log 2 minus e power 2 log 2. But now you can go back to 2 power, right. So, 1 by log 2 times, this is e power, this is the same as 2 power 5 minus 2 power 2. So, it is 35 minus 4, 28. So, 28 by log 2. Okay. So, it is very easy to do. Once you convert to e, everything becomes very easy. So, 2 power x you can do like that. Okay. And what about log x? Okay, just log x. What do you do here? It looks a little bit complicated. You have to do by parts here, it turns out. So, so integral 2 to 5 log x dx. Okay, log x has a easy derivative, but then it does not have I mean, there is nothing else you can do here. You can't put u equals log x, nothing much will happen here. The trick is to do by parts. By parts, you remember, I hope you remember by parts integral. So, what is by parts? Integral u dv is uv minus integral v du, right. So, this is by parts, the way you have to think of it. So, what is v here? You simply take v to be equal to x. Okay, so, it is log x dx. So, this is the same as x log x between 2 and 5 minus integral 2 to 5 x times d log x. Okay, so, this is parts, and parts will give you the answer very easily. So, x log x 5 to 2 is very trivial. It is 5 log 5 minus 2 log 2. Here integral 2 to 5 x times, what is d log x? This I know, right, dx. So, this 2 will cancel. This will just become 5 minus 2, which is 3, and you are done. Okay. So, it is very easy. So, basically antiderivative, this is something that a lot of people tend to remember, of log x. Antiderivative, derivative is 1 by x, antiderivative is x log x minus 1. Okay. So, in fact, if you take a derivative of this, okay, x log x minus x, I am sorry, that is where I made a mistake, x log x minus x. If you take a derivative here, notice what happens, x into 1 by x plus log x into 1 minus 1. So, these two sort of cancel and you get log x alone. So, this x log x minus x is the antiderivative of log x, and that you get by doing parts. Okay. So, you can use the parts method very traditionally and find out that this is how it will work. Okay. So, that is about just integrating log. So, remember parts also, you may have to use it sometime. Here there is a base 2, you know what to do, you just convert to base e, it is a constant times this integral, easy to see. Here is 1 x power 2x into 1 plus log x. We saw this before, it is a little bit complicated, but if you do u equals x power 2x, the problem will become very easy. We just now saw this, but let me do it for you. If you do integral 2 to 5 x power 2x times 1 plus log x dx, the substitution to try always, I mean the first thing to try is x power 2x, and what will be u prime log u is 2x log x, and then 1 by u du is this one is just 2 times 2x times 1 by x plus 2 log x times 1 dx, right. So, this would cancel and you get du equals du by u equals 2 times 1 plus log x dx. Okay. So, So, this is important. So, this integral just becomes integral 2 to 5 u times this would be du by 2u, right, and that u would cancel. So, you just get so I'm sorry, it is not 2 to 5, but to do the substitution. So, 2 power 4 to 5 power 10, okay, so it is pretty large numbers, and then u and u will cancel and you get half 5 power 10 minus 2 power 4. So, quite a large value for the integral. Okay, so hopefully you saw this substitution. So, whenever you have x power 2x and all, definitely try the substitution. There is this 1 plus log x that magically appears. It has been made so that this integral can be derived in closed form. Okay. So, that was a quick run through of all the uses of logarithms. I will urge you to go pick up some problems either in OpenStax and so many other books that we provided you as examples. You go try a lot of these problems on your own, and then you will get a degree of comfort with the log function, and the log and the exponential and the various ways in which you can do limits and derivatives and integrals with log are very, very important. Okay. Thank you very much.